Okay, so today we're looking at, what we're looking at here is really a component of electrophilic aromatic substitution reactions. But specifically, it's about electron donating groups attached to these benzene rings. And we're wondering, well, why are they ortho-para directors? And I think there are a few ways to think about this. But the way that I know best and that works for me best is through resonance. So if I can show you what I mean, we've got a benzene ring here, right? And let's attach a methoxy group to it. So if you can't see that, that's an oxygen attached to another methyl group that's on the benzene ring. And what happens here is we've got two lone pairs on this oxygen here, and what it is actually capable of doing is donating, like it says, it implies, donating electron density back into that ring. And so how that happens is we've got an arrow pushing the electrons down between this carbon and the oxygen here, right? And so that makes a resonance structure in which, if you would just give me a little second, oh my God, that's too small, I'm so sorry. Just give me a second to draw this. Right? Sorry, I don't have very good drawing skills. But what happens is, and I shouldn't have drawn these double bonds in. What happens is, you've now got a double bond, but what you're going to notice is that, oh, there's too many bonds in this carbon, and I should have drawn that in already, to be fair. So we will take this double bond, we're going to break it, and we're going to place the electrons from that double bond, specifically the pi bond part of the double bond, onto this carbon here. And so now we've got a negative charge on that carbon there. And one thing that I maybe should have mentioned before is, I don't have my other color. Oh, it's right below me. So these ortho and para are relative to a substituent, which just means that it's not a set point on the benzene ring. It's relative to our attached methoxy group. So these positions right here, both of them are the ortho position. And the one opposite to the methoxy group, that's the para position. Now, of course, this would be different depending on where you place the methoxy. Right beside, ortho. Opposite side, para. Okay? And so, but I've only showed you one resonance structure so far. And, well, you know based off electrophilic aromatic substitution that the benzene ring is the nucleophile. So it is attacking whatever electrophile we place into that mixture, right? So when this position is more electron rich, it enables it to be a nucleophile, even more so than usual. So that's why it will react at the ortho position. But if we want to know what the para position is, we can continue pushing electrons and making resonance structures. So what we would do is we would take this bond and we are going to, well, actually what we do is we take this one up here, this pi bond, and we're going to place it onto the carbon there, and we are going to move this charge back into a pi bond. So excuse me if I'm blocking the view. For 1 second. And my apologies, I did forget to place a positive charge on this oxygen, right? Because that's what's going to happen when one of its lone pairs leaves to form a pi bond. And so we can see now this position is enabled to react in a nucleophilic manner. And it's going to attack that electrophile, right? And so there's really no need to draw another one, but I will, just to show you that both ortho groups are capable of reacting, even though it's a symmetrical molecule, so they're the same thing. I will show it regardless. So what's going to happen is this pi bond is going to get pushed onto this carbon because it can't get pushed over here again, and then we have a pentavalent carbon. We'd have too many bonds on our carbon. We can't have 5. So what's going to happen is the lone pair that's on here, because when I put a minus charge on a carbon, what that really is it's got a lone pair, right? This is just an easier way to represent it. When I push it down here, we're going to see oh my God. Okay. Oh my God. Sorry, I totally messed up this drawing. Give me a second to just wipe that off the board. Even that's terrible. I'm so sorry. Minus. We're just going to roll with it. OME. Right? And so you can see that both ortho positions are negatively charged in these resonance structures. And of course, these structures are all representations of a resonance structure, meaning that none of them are totally correct to what the actual picture is. The actual picture, I mean, the electrons are delocalized, but there maybe is a partial negative charge at the ortho and para positions, and that enables it because a nucleophile is stronger when it has more electron density, right? So, yeah, I mean, think of your classic electrophiles. You have, you know, bromine is often an electrophile, of course. If it's going to react with a benzene, it requires a catalyst. Chlorine, obviously they have to be ionized to have a positive charge. But yeah, that's the gist of why EDG groups are ortho-para directors. I hope this has been a little bit helpful. I don't know, I hope I haven't been blocking everything, and I hope it's been a little bit helpful. So yeah, thanks for watching.